Hello, and thank you for joining me. My name is Derek Kane, and today we're going to talk about decision trees and random forest models. This presentation is part of a broader series of lectures related to data science, predictive modeling, statistical analysis, and machine learning. If you're interested in learning about these topics more, please feel free to go through and look at some of the previous presentations. All right, let's begin. The overview of topics which we'll go through today is we'll start with an introduction to decision trees. What are they, how do they work, and the importance of them. We'll start discussing cart models, which are a form of decision trees, conditional inference trees, ID3 and C5.0 decision trees, and random forest algorithms. Then we'll get into the topic of model evaluation metrics, and then shift into a practical example of applying this machine learning technique. We're going to use the machine learning technique to help identify diabetes and also identify factors which contribute to customer churn. Decision trees, or recursive partitioning models, are a decision support tool which uses a tree-like graph of decisions and their possible consequences. A decision tree creates a type of flowchart which consists of nodes, which are referred to as leaves, and a set of decisions to be made based off of the node, which is also referred to as branches. The leaf and branch structure forms a hierarchical representation that mimics the form of a tree growing. Decision tree learning is one of the most widely used and practical methods for inductive inference and is an important tool in the machine learning and predictive analytics toolbox. Here are some applications of decision tree models. In a manufacturing capacity, evaluating chemical materials for production purposes. In a production sense, optimizing processes in electrochemical machining, for example. In biomedical engineering, decision trees are often used for identifying features to be used in implantable devices. Astronomy uses decision trees for filtering noise from the Hubble Space Telescope images. In molecular biology, decision trees are used to analyze amino acid sequences within the Human Genome Project. Pharmacology has applications in the analysis of drug efficacy. Decision trees are also used in planning and scheduling of assembly lines. And finally, decision trees are used in medical applications, such as an analysis of the sudden infant death syndrome, or SIDS. So decision trees are very useful and very broad, and they can cover pretty much any area where we have good, high-quality data available. Some advantages of using decision trees are that they're very simple to understand and interpret. People are able to understand decision tree models after a very brief explanation, and in their simplicity lies their strength. They have value even with little hard data available. Important insights can be generated based on experts describing a situation, its alternatives, probabilities, and costs, and their preferences for certain outcomes. So flowing a decision process through a decision tree has value, and there are important insights to be gained from there. The machine learning algorithms themselves are robust to noisy data and capable of learning disjunctive expressions. And what's nice is that decision trees can be used to help determine worst, best, and expected values for different scenarios. There are some disadvantages of decision trees that should be noted. For data including categorical variables with different number of levels, the information gain in decision trees are biased in favor of those attributes with more levels. So if I have variables that have high, medium, and low, or many different categories or hierarchies within, the trees tend to grow in favor of those type of variables. They kind of grow towards the sunlight, if you will. Calculations can get very complex, particularly if there are many values which are uncertain and or if many outcomes are linked to each other. A classification tree searches through each independent variable to find a value of a single variable that best splits the data into two or sometimes more groups. Typically, the best split minimizes impurity of the outcome in the resulting data subsets. For these two resulting groups, the process is repeated until a stopping criteria is invoked. One example of a stopping criteria might say that we need to have a minimum number of observations in a node. So here's an example of a very simple decision tree. Okay, I have one node on the top, two branches, and then I have two nodes at the bottom. Here is an example of a slightly more complex decision tree. So if I look at the example on the left-hand side, I see that if it's less than 45,324, then flow to the left. If it's greater than that number, flow to the right. But in our more complex example, we see that if I'm less than 45,324, then I hit another decision point, and it says, okay, well, if that's the case, and I'm less than 0.60, then I'm going to continue going left, otherwise I'll go right. So this is a visual representation of a decision tree. What I like about this graphic is it depicts how a classification decision tree is constructed. So if we look at our root node, we see that there are two different classes that can be used as the input for the splitting criterion. And they call this, X% or Y%. From this data point, we have to find a clean split. So we split the data, and we say on the left branch, I'm going to emphasize maybe the Y variable or the Y percentage. On the right side, I'm going to emphasize the X percentage. So then a decision criteria is brought in, and if we look at the distribution of the results of flowing through the branch down to the next layer of the nodes, we see that most of the values have that Y percentage on the left-hand side, and on the right-hand side have the X%. So I like this because it kind of shows the flow of information throughout a decision tree behind the scenes. Well, what are some examples of the splitting criterion? We talked about splitting between, creating a two-part split. How do we go about this? Well, we can look at a minimum number of observations. We can say, okay, I need to have, at least 10 observations in a node, and that's, one way we can go about it. Another way is through what's called the information gain. And what information gain is, it's an impurity-based criterion that uses the entropy measure, as derived from information theory, as the impurity measure. So entropy, most people think of it in terms of the second law of thermodynamics, and that's essentially going from ordered state to increasingly disorder, and entropy is the measure of the increase in disorder. But it also has applications in terms of the understanding of systems and information. Okay. We can use another component called the Gini index, which is another impurity-based criterion that measures the divergences between probability distributions of the target attribute's values. And an additional approach is what's called the gain ratio. And that normalizes the information gain by taking the information gain divided by the entropy. So it's very similar to the information gain, except for it's a normalized form. So when we're growing a tree, how do we know what size of a tree we should be looking at? If we employ very rigid stopping criteria, it tends to create these smaller, underfitted decision trees. So, like little tiny twigs growing out of the ground. On the other hand, if we don't put very strong stopping criterion, we're going to have a bush that just kind of grows wildly, and there'll be lots of branches and nodes, and some might think that this is good, but what happens is it becomes more overfitted to the training data set that we're working with. So to account for this, we have to come up with pruning methods, and there are some methods suggested by Bremen to help solve this dilemma. And the basics of this methodology is that you let the tree grow in a kind of wild sense. It grows to a certain point, and then we take it and we just prune it and cut it back by removing branches in a more systematic way, and just cut off those branches that aren't helping the model improve the generalization accuracy. I'm often left with the question, well, how many nodes and branches are acceptable for a decision tree? What's a good number of branches, and what's a great way to find this out? Well, trees are typically indexed by their depth, and the classical decision tree methodology uses the cost complexity parameter, or CP, to determine the best tree depth. The intention is to identify the lowest CP value, which guides us to the appropriate tree size. So if we're looking at this graph here, the size of the tree is at the top, and each point is corresponding with a tree of a certain size at a relative CP level. In our example, a tree of size 4 has the lowest CP value. However, the principle of parsimony tells us that a tree of size 3 would also be adequate. I want to take a look at how this pruning works, and we can see the evolution of pruning over time. So imagine, if you will, I have a very complex, bushy decision tree here. If I look at the accuracy as a function of the CP parameter, I just have one dot. As I go about systematically pruning my model, we see that the accuracy goes up over time. Okay, it dips down a little bit, and then it begins to ascend to a certain point. However, if I continue to prune beyond this point, we run into issues. Okay, so pruning too much actually will result in a decrease in accuracy over time. And I'd like to thank these diagrams and image from Max Kuhn, who is the developer of the carrot package in R. Really brilliant mind in data science and statistics, and he really has covered a lot on decision trees. Well, there are a number of different types of decision tree algorithms that can be used for machine learning. The calculation process utilizes recursive partitioning algorithms to create the splits. These type of models are commonly referred to as CART models, or classification and regression trees. We need to first look at the characteristics of the data set through our EDA procedure, which we had talked about in previous lectures, to assess the dependent variable. Is this variable categorical or continuous in nature? If we're predicting a categorical variable, we'll use a classification tree. But if it's a continuous variable, a numeric variable, then a regression tree outcome. Then we have different types of algorithms that can be employed depending on the circumstance that we're working on. We'll first talk about CART modeling in the classification tree. So this modeling approach is used to determine outcomes in a categorical nature. This would be a variable with a dichotomous outcome, a yes or no, or a 0 or 1, or in some instances, cases with multiple category levels, such as high, medium, or low. The example image that I'm showing here shows a CART model being applied in the medical field that is detecting whether a type of deformation called kyphosis is present or absent after a surgery. So depending on how you answer a series of questions, at the end of the decision tree will tell you if kyphosis is present or absent. And this is an example of a classification CART model. A different type of CART model and approach is used to determine outcomes that are in continuous nature. This could be a dependent variable with a range of values from negative infinity to positive infinity. The example here shows a CART model being applied in the automotive industry. And this model is looking at how variables such as price, car type, reliability, and country of origin are related to miles per gallon. So if I take a look at the decision tree on the left-hand side, I can say if my price is less than $9,446, then I'm going to have a miles per gallon equal to 32 by looking at that root or the bottom layer of nodes. That's what the numeric values are representing. This miles per gallon variable can take a value of 0 to infinity. So you're not going to have a mile per gallon that's a negative value. But there is no upper limit on it, and because there's no upper limit, we would use a regression model for our decision tree. A different class of decision tree models are what's called conditional inference trees. The manner in which CART models decides what variable to include at each branch can potentially create a variable selection bias. So we've talked about using information gain and the gain ratio and Gini index for creating the splits, okay, and that creates a selection bias. A conditional inference tree uses a significance test procedure in order to select variables instead of selecting the variable that maximizes an information measure. So this is a statistical based approach for deciding how to grow a decision tree. This approach uses a covariate selection scheme that is based solely in the statistical theory. Again, here is an example of our decision tree for our kyphosis example. I now want to spend a little time discussing a couple other decision tree algorithms that are worth looking into. The first one is the ID3 algorithm, and this algorithm uses information gain as the splitting criterion. The way that the tree works is that the growing stops when all of the instances belong to a single value of a target feature, or when the best information gain is not greater than 0. ID3 does not apply any pruning procedures, nor does it handle numeric attributes or missing values. The C5.0 algorithm is the evolution of the ID3 and was developed by the same author, Quinlan. This approach uses the gain ratio as the splitting criterion. The splitting ceases when the number of instances to be split is below a certain threshold. Then error-based pruning is performed after the growing phase. This algorithm can handle numeric attributes well. It can induce from a training set that incorporates missing values by using the corrected gain ratio criterion. The approach contains built-in features to handle resampling and boosting. The C5.0 algorithm has been in use successfully in commerce for decades. Only in recent years had the proprietary source code been released to the general public. So this is a very powerful proprietary algorithm that has been used in business applications that are now readily available to us and can be used for predictive analytics and machine learning. I'd like to talk a little bit about some of the pros and cons of single decision trees. Trees can be computed very quickly and have simple interpretations. This is a great thing. So it doesn't take a lot of computing horsepower to develop these trees. And you can put a decision tree in front of many people and they will understand it. They have this built-in feature selection. So if a predictor was not used in any split, then the model is completely independent of that data. That's great. Unfortunately, trees do not usually have optimal performance when compared to other methods. I don't want to say that they're terrible predictive algorithms, but there are just so many other methods that are readily available that outperform decision trees. Additionally, small changes in the data can drastically affect the structure of a tree. This last point has been exploited actually to improve the performance of trees via ensemble methods, where many trees are fit and predictions are aggregated across the trees. Some example of these ensemble methods and the exploitation of this feature are through bagging, boosting, and random forests. We're going to get into that in a little greater detail in the upcoming slides. First, I'd like to talk about boosting algorithms, and the method is used to boost single trees into strong learning algorithms. One way I like to think about this, or I visualize it, is Popeye eating his can of spinach. So Popeye is the decision tree here, and he's going to eat some magical substance, and all of a sudden he's going to be a really strong tree. Okay. And what boosted trees are trying to do is they're trying to improve the model fit over different trees by considering past fits. So a tree grows and it lives its life, and it does certain things very well. Then this tree dies and is replaced by another tree. And this tree, in a sense, has learned, what worked well for the last tree, what didn't work well, and it's incorporating that knowledge in its in the way that it's being built. Now, there are many different approaches to boosting that include the AdaBoost for binary response, and there's stochastic gradient boosting. Definitely explore these different techniques. If you're interested in understanding the mechanics of a basic tree boosting algorithm, here is an example below, provided by Max Kuhn. So let's talk about random forest models. A random forest algorithm takes the decision tree concept further by producing a large number of decision trees. This approach first takes a random sample of the data and identifies a key set of features to grow each decision tree. So we take random variables and we say, let's grow a decision tree. And then we evaluate the performance of that tree. And we say, okay, now let's take another random set of features and let's grow a second tree. How did this tree perform compared to the first tree? And it continues to iterate through this process. And eventually an entire forest is produced of these random features, hence the name random forest. Okay. These decision trees then have their out-of-bag error determined, which is the error rate of the model. And then the collection of decision trees are compared to find the joint set of variables that produce the strongest classification model. An example of the process flow is depicted below for a random forest. We have our sample data that is then pushed through to train, or we split the data to create a training set of information. From this training set, we find the features that we want to look at from the algorithm. Then we grow our tree and loop through this process over and over until we've grown the amount of trees we want to look at. And then we create a calculation of the estimate of the out-of-box error. And then at the end, we evaluate the entire collection of trees as a single random forest. When you look at the entire performance of the forest as opposed to individual trees, one way to visualize it is through this graph here. We can see on the left-hand side, this is the error rate. And the error rate is going down as we're producing a greater number of trees, and then it kind of levels off. So when we get to about 100 trees in this instance, we're really not getting that much more performance, but it is having a much better error rate than just a single tree alone. So this demonstrates the power of a random forest model, and random forest models are an extremely powerful ensemble learning technique. So how can we estimate the performance for classification? So far in the series of lectures, we've talked about evaluating regression analysis, but we never really got into performance measurements for classification exercises. I think this is a great area to dive into this topic because the most common application of decision trees is within classification. The manner in which we evaluate the performance of classification algorithms is distinctively different than continuous models. Okay, there's different aspects of it. Because we know the correct class of a data, one common metric that is used is the overall predictive accuracy. So if I have 10 data points and I know that yes or no, a dichotomous variable is the attributes of that data, then I can say, okay, well, did I predict a yes or a no? And then I can compare those two. However, this approach of saying, okay, what the percentage of predictive accuracy just based off of the amount wrong can sometimes be problematic when we don't have balances in the class. The kappa statistic takes this into account and then calculates the expected error rate, where O is the observed accuracy, E is the expected accuracy under a chance agreement. Now for two-class models, my yes-no example, there's a very powerful metric that we'll get into called the receiver operating characteristic, or ROC curves, and they can be used to characterize model performance. Before we get into the topic of ROC curves, I want to introduce the idea of a confusion matrix. And a confusion matrix is a way to represent a categorical variable. One example is a dichotomous 0-1 variable. And we show this in a cross tabulation, which allows us to see how well a model has performed. The left side of the matrix shows the actual scenario based on historical data, and the top shows the predicted results of the model that we're evaluating. So we create our decision tree model, and we want to say how well did it classify. On the left-hand side, we see the actual response. So in this example, we're looking at mushrooms, and we know that certain mushrooms are edible, and we know that other ones are poisonous. So our decision tree algorithm in this case is predicting whether or not a mushroom is going to be edible or poisonous. So this is really a handy way of showing the true positive, so the cases in which we have actual edible mushrooms and we're predicting edible mushrooms, against the true negative, so actual poisonous mushrooms and we're predicting that they're poisonous mushrooms, against the false positive and false negative rates for the model's performance. And what's important to notice here is that we have what's called the off-diagonal. And in this case, it's highlighted by this green circle. And I put the text as green and red to kind of visually indicate that green is good and red is bad. We want the number of observations to fall in this off-diagonal. Okay, so if we have most of our values sitting in this area, then we know we're, from a very broad sense, we're going to have a pretty good predictive model. In order to perform an ROC analysis, we need to calculate some figures based off of this confusion matrix. Okay. It's highly unlikely that we're going to create perfect predictive models from the data that we have available. There's going to be misclassifications and prediction errors, and we have to consider this in the performance evaluation. Specificity and sensitivity are statistical measures of the performance of a binary classification exercise and are a critical component to the ROC analysis. They represent aspects of the modeling error. So specificity is the true negative divided by the true negative plus the false positive. And what this means is that given that a result is not truly an event, what is the probability that the model will predict negative results? Sensitivity, on the other hand, is we take the true positive divided by the true positive plus the false negative, and can be interpreted as, given that a result is not truly an event, what is the probability that the model will predict event results? And we can calculate some additional metrics such as the false positive rate, which is 1 minus the specificity. Now that we've talked about these components and aspects of a confusion matrix and some of the metrics, we're ready to take a look at a receiver operator curve. The ROC can be represented graphically in two dimensions as the relationship between sensitivity and the false positive rate. This is typically referred to as the lift, if you will. The area under the curve is a representation of the ROC in a single scalar. Now, let's focus our attention at the actual graph itself, and I'll explain what this means in simple terms. If I'm looking at the chart, I see this very large red diagonal line. And this is the line in which we don't want our observed line to fall below. This is our threshold value. And this represents an area under the ROC curve of 0.50. And what this implies, the area under the curve, is that if I was to take a coin and flip it, what is the probability that I'm going to get heads or tails? Well, it's 50%. Okay, it's pure random chance. I have one of two outcomes. 0.5 is the probability. That is the same thing as this line. Okay. So when we create our predictive model, it's going to produce the line that's blue. And what we want this line to do is we want it not to be flat up against the red line, but we want it to be more elastic, and we want to kind of pull it further up to the left-hand corner until it matches where this green line is showing, which really is the area under the ROC curve of a 1, which is a perfect prediction. So the ROC area of our blue line, in this case of 0.60, can be interpreted as a prediction that is 10% greater than random chance alone. Now, is the prediction of 0.6 a great prediction? Well, it depends on the application. Much like our discussion previously in the linear regression analysis tutorial about R-squared, it depends on the application. And one thing that we definitely don't want to see is if that blue line dips below that red line, then essentially your predictive model is performing worse than random chance. You're actually better just randomly flipping a coin than using the predictive model that you've built. So you definitely don't want ROCs or the area under the curve less than 0.5. That's really bad. There's another concept that can be used in conjunction with a confusion matrix that I want to touch upon here, and this is what's called a cost matrix. Another interesting way to evaluate the strength of a model draws from the confusion matrix concept and into what we call a cost matrix. In real life, there's a cost for failure. If I'm going to make a predictive model and I'm wrong for my prediction, well, it depends on the type of prediction that I'm doing and what the cost is. For example, if I eat a poisonous mushroom and I think that it was edible because my predictive model told me it was edible, well, this is going to kill me. And that's really bad. The cost is extremely high for being wrong. However, if I predict that a mushroom is poisonous when it is in fact edible, well, the cost is less severe. Maybe I lose out on a tasty meal, but I'm not dead from my other prediction. So we can take the values of our observed results from our confusion matrix, and we can extend them by this cost matrix. So I can take, the cost of the true positives times 1, or the cost of the true negatives times 4 against the cost of the false positives and false negatives, and I can sum that up, and that gives me an overall cost of my predictive model. And we can calibrate these type of models to try to reduce the errors in the different class, reducing the specificity or the sensitivity, and take that into account. So cost matrices are really powerful tools that can be used in conjunction with ROC and in this type of analysis. Now that we've spent some time going over an overview of decision trees, I want to shift the focus and go back into a practical example of the application of decision tree models. Before we begin, let's go ahead and try to understand the data that we're working with. In the medical field, there are many applications of decision tree models which can aid in diagnosis and identification of treatment protocols. The dataset we will be working with contains information related to patients who have been diagnosed with type 2 diabetes. The goal for this exercise will be to build 2 predictive models. We're going to build a cart model and a random forest model to assess the variables related to predicting diabetes. Here is a view of the variables within the dataset. The dataset contains 768 observations and contains various measurements such as number of pregnancies, BMI, age, and the variable of interest for us, the dependent variable, is the class variable, and that represents whether or not somebody has diabetes or not. So we want to use this set of information to make the prediction onto the class variable. After splitting the data into a training and testing set, we built a cart model without pruning on the training set and evaluated the performance on the test set. We did this intentionally, just to kind of see what kind of animal are we working with here. And the classification tree that has been produced is an extremely deep example. There are 10 levels of depth, and it's a very complex example. If I look at the ROC chart, which we talked about, the area under the curve is showing a 0.7791, which is pretty good. So we're saying 28% improvement over random chance alone. Now let's focus on pruning this tree. So we calculated the CP metric, and we determined that a tree of size 2 would be sufficient. Okay, and here's the output of that graph, just for those who want to see, and we're selecting the lowest value. In this case, our decision tree is very simple. It's one question. Is my plasma level less than 144? If it is less than, you're not going to have diabetes. But if it's greater than 144, guess what? You have diabetes. Interestingly, the overall performance was unaffected after the pruning procedure was performed. When we look at the ROC chart, it's exactly the same, 7791. Now, I've created a confusion matrix here that shows the observations, and we can look at some of the other metrics, such as sensitivity, specificity, the overall predictive accuracy, to get a better sense of the performance characteristics. So instead of having a fairly complicated model, we've been able to prune it down to a simple, single question that can determine diabetes with fairly high accuracy. Now, let's build a random forest model. This model that we're going to build it with 500 separate decision trees. And we're going to define that we want 5 variables included at each split. When we run this, the OOB estimate of the error rate is 26.03. Now, what's interesting is we can actually run a couple of charts in R that allows us to identify the most important variables. And we can do this either through using mean decrease accuracy or the mean decrease Gini. And I've placed some blue vertical lines as just kind of a cutoff to show really where the most important variables are in this case. And much like our decision tree that we had before, we see that the plasma level is a very significant variable. We see that BMI is also significant, and age. If we look at the mean decrease Gini at the bottom, we also see plasma level and BMI and age as well, but not as much. So these 3 variables are what we consider to be important risk factors for diabetes. We know that overweight people and people who don't take care of themselves and are eating junk food and sugary foods all the time are going to have a higher BMI and are at a greater risk for diabetes. But likewise, your age also increases your risk. But most importantly, we see that our plasma levels is by and large the most important variable in this case. The random forest model has an area under the curve of 84.67 compared to the area under the curve of 0.7791 for the CART model. That's a notable improvement between the two, and now our predictive accuracy is getting even stronger. Likewise, we can see some of our performance characteristics in our confusion matrix. We can check out our sensitivity and our specificity and overall predictive accuracy. So the trade-off from interpretability of using a random forest model, which is much more complex, is that it has a higher accuracy. If we want a simpler model that's easier to explain, well, we can show it, but at the same time, it's not going to be as powerful of a predictive algorithm. Another example that we're going to look at deals with customer churn at telecommunication companies. First, before we jump into the example, let's understand a little bit about the scenario we're in. In a competitive business environment, a lot of effort is spent on attracting and maintaining customers. The cost to maintain an existing customer is much less than the cost to acquire them. This makes it paramount for organizations to understand what factors contribute to the turnover of clients and enact preventative strategies to reduce turnover. This turnover is often referred to as the churn or the churn rate. The data set we will be working with contains information related to cell phone subscribers and churn, and contains a variety of information related to their churn. Our goal for this exercise will be to provide a predictive model that can be leveraged to help understand and leveraged to mitigate customer churn. So not only are we going to create a predictive model here, we're going to try to derive insights and use this to help reshape our strategy. Here is a view of the variables within the data set. Now, looking at this data set, we have variables like the state, the phone number, certain plans that they have, whether or not they have voicemail, the number of voicemail messages that they're using, what their minute usage is, what their daily charges are, the total number of customer service calls, and ultimately what their churn rate was. Now, the total day minute, total day call, total day charge, those 3 variables, we can actually further break them down not only by day, but we can break it by evening, night, and international. I'm not showing all of those columns on this slide here just because I don't have enough real estate to really show it very cleanly, but there are additional variables in the data set. Our goal is we're going to develop a C5.0 decision tree model using the churn variable as a dependent variable. When we apply the C5.0 algorithm in R, we're able to get a number of different performance metrics such as percentage of error, attribute usage, and a confusion matrix. So here is our confusion matrix from our churn example. As we can see here, we can find with very high accuracy, 96.2% accuracy. Additionally, we understand what attributes are used in this model and to what degree. What are the most important characteristics? And finally, we have a very plain text-based decision tree model. Now, we can dress it up and make it a little fancier, put some a nice glossy coat of paint and show a nice tree, but what's important is the content of the split of the nodes, the branches, and how to arrive at each one of the decision points. The C5.0 algorithm contains a feature which allows for an export of the rule set generated by the model. Let's review some of the results for potential business insights. So here are the rules, some of the rules that are produced, and I just want to go through them a little bit. If I have a voicemail of no, and my total day minutes is greater than 245, and my total evening minutes is greater than 201, and my total night charge is greater than 8.54, and my number of customer service calls less than 3, I'm going to churn, which means I'm going to leave the organization. I'm going to take my business elsewhere. If I don't have an international plan, I don't have a voicemail option, my total daytime minutes exceeds 260, and my total evening minutes exceeds 184, I'm going to churn. The last one is if my total daytime minutes is less than 160, if my total evening charge is less than or equal to $19.83, and my number of customer service calls is greater than 3, I'm going to churn. So these are very programmatic points, but I think if we peer underneath the surface and really start to look at what the data is showing, we can find some business knowledge there. There seems to be a pattern emerging that at least I've noticed, is that if a cell phone user exceeds 240 daytime minutes and 180 evening minutes, that they are likely to churn. Perhaps this is pricing of a rate plan that is too high. Maybe customers are sitting in a certain type of rate plan that just doesn't fit their needs. Perhaps all we need to do is include a voicemail option in the package. Give them an additional feature that keeps them happy. Not surprisingly, we also see that if a customer makes 3 or more service calls, they're likely to discontinue the service. I don't know about your experiences, but whenever I have to call customer service, for whether it's for Comcast Cable or AT&T, it's usually not the greatest experience. And if I have to do this many times over, I eventually will get frustrated and I will leave and take my business elsewhere. So we're seeing this corroborated in the data itself. The rule set that we had produced offers tangible evidence towards predicting behavior based off of product usage and consumption, and drawing from machine learning techniques. To build off of this analysis, we can consider understanding the demographics of customers who fall within these rule sets. What is the age range of these folks who are churning? What's their income level? Marital status, number of children, if they have children, their education level. Are they blue-collar or white-collar workers? What is their ethnicity and race, etc., etc.? Once we understand these characteristics and compare this against the population, perhaps we can even employ clustering algorithms. We can begin to frame the business strategy and drive behavior we want to perform in the marketplace. So if we see individuals are leaving that are at a certain income level and education level, we will create a marketing campaign that targets those individuals specifically. And so through the knowledge that we're gaining from our decision tree models and our rule set, we're turning this into actionable business intelligence and drawing from predictive analytics. I'd like to thank everyone for joining, and I look forward to continuing going through the presentations. Thank you.